A nuclei is a bound system. If you were to break apart this bound system by breaking the nuclear bonds between the protons and protons and protons and neutrons and neutrons and neutrons, you would need to supply energy to separate these nucleons. The binding energy is denoted with an E subscript B, and it's the energy that we must supply to separate a nucleus into its constituents, to disassemble it into all of its individual protons and neutrons. It is found experimentally that the mass of the nucleus is less than the total mass of the protons and neutrons combined. The mass difference, delta M here, is often called the mass defect and is denoted with a delta M. So delta M equals Z, which stands for the number of protons, multiplied by M sub P, which is the mass of the proton. So this would be the total mass of all the protons in this nuclei, plus N, which stands for the number of neutrons, multiplied by the mass of the neutron. So this term would really be the mass of all of the neutrons, minus the mass of the nuclide. What you find is when you add up all the mass of all the constituents, that will have more mass than the mass of the nucleus by itself. If we take that missing mass or mass defect and we use Einstein's mass energy equivalence formula, E equals m times c squared, you'll get the binding energy. Another way to think of the binding energy is basically to think of it as how much energy is needed to hold this nucleus together. The concept is similar to ionization energy in the atomic physics section. Remember when we studied that we had these energy levels, and if we were to think about the amount of energy that would be required for an electron to be removed from its ground state so that it is no longer bound to the atom, that energy was called the ionization energy. So it's kind of similar idea. In the next example, you're going to be asked to find the mass defect, the binding energy, and even the binding energy per nucleon.